Let us start today's class. Last class we have studied about time independent Schrodinger equation. In that we have taken the wave function of a system as a into e raised to, it is written here, a into e raised to 2 pi by lambda into I into x. And otherwise if we consider, here we consider time is equal to 0. For finding time independent Schrodinger equation, we need to take the wave function which is not depending on time. That is, we have taken time is equal to 0 there. So otherwise the wave function is psi is equal to a into e raised to minus I by h cut into et minus px. I don't remember whether I have explained the terms in that equation. The terms E means its energy, T is time, and P is momentum, X is the position. So this is the normal equation for a wave. So you have to remember this equation. It is the equation for a wave which is depending on position and time. But if you are not considering the time dependence, that is, if you consider T as 0, then you have to just take psi of x. T time is equal to 0. Psi of x is equal to a into e raised to 2 pi by lambda I into x. That is a into e raised to I minus I by h cut into, a into e raised to plus I by h cut into px itself. So p by h cut means it is k. K is, what is k? K is the wave vector which is 2 pi by lambda. So we know the equation h cut k is equal to p. H cut k means h cut into the wave vector. Wave vector is 2 pi by lambda. So you can simplify it to get kx, a into e raised to I kx. You can write the wave function psi as a into e raised to I kx. Here we have written the expanded form of k also. It is a into e raised to 2 pi by lambda into I into x. So remember that. Actually it is a into e raised to plus I by h cut into px itself. It is same. Both this equation a into e raised to 2 pi by lambda ix is same as a into e raised to I by h cut px. Okay. So now we are taking the first equation, psi xt is equal to e raised to minus I by h cut into et minus px, where we consider the time and position variable both. So let us go to the Schrodinger time dependent wave equation. So we have taken the wave function here, a into e raised to minus I by h cut et minus px. Okay. So now let us we know that E is the total energy and P is the momentum of the particle. Now differentiating with respect to x first. So this is having a variable time and position. So t and x are variables there. First let us take the derivative double time, dou square psi by dou x square with respect to time, with respect to position. So dou square psi by dou x square is minus p square by h cut square into psi. So if it is one time dou psi by dou x, what will be the value? A into e raised to minus I by h cut et minus px into minus I by minus I into p by h cut. That is first derivative with respect to x. So if you do again one more time, it will be a into e raised to minus I by h cut et minus px into p by h cut. It will come two times. I p by h cut means p square minus p square by h cut square. I square is minus 1. So it is minus p square by h cut square into psi. Understood? Okay. Now we rearrange it. P square psi is equal to minus h cut square into dou square psi by dou x square. Now let us do the differential of psi with respect to time. So dou psi by dou t, first derivative, it will be minus I e by h cut into psi, isn't it? Minus I e by h cut is constant, which is coming with the time. So this can be taken out. Minus I e by h cut into the same psi equation, a into e raised to minus I by h cut into et minus px. So you can write like that. Now rearranging, E psi is equal to I h cut dou psi by dou t. Now when we take the non-relativistic case, total energy is kinetic energy plus potential energy. So it is P square by 2m plus V. P square by 2m is half mv square itself. P ke mv kodukkuvaanengi, so it will be half mv square, which is kinetic energy. So E is equal to half mv square plus V. Now E psi, so now we are this is an operator equation. I will teach you about operators later, but you just add psi in all terms. So E psi will be equal to P square by 2m psi plus V psi, isn't it? Now let us write using equation 2, 3 and 4. So P square, instead of P square we substitute as minus h cut square dou square psi by dou x square. So it will be minus h cut square by 2m dou square psi by dou x square. V psi we have written it like that itself. E psi is I h cut dou psi by dou t. Okay, so this is now the new Schrodinger equation, which is depending on time. So I h cut dou psi by dou t is the left hand side, which is depending on time, and the right hand side, which is completely depending on only on position. So this is the time dependent Schrodinger wave equation in one dimension. If it is in 3 dimension, how will you write? You can write it as I h cut dou psi by dou t is equal to minus h cut square by 2m del square psi. Instead of dou square by dou x square, you can write as del square. Del square is dou square by dou x square plus dou square by dou y square plus dou square by dou z square of psi, operating on psi, plus V psi. You will get that equation, which is 3-dimensional time dependent Schrodinger equation. Now let us move to linearity and superposition. So let us have a wave function or two solutions of a Schrodinger equation. So this is the above equation is a Schrodinger equation, time dependent, isn't it? So the solution for this is Schrodinger equation is psi. Okay, so that psi we are taking as a solution, and if you have two Schrodinger equation, you will have let it be psi 1 and psi 2 are the solutions. So if you have two solutions, psi 1 and psi 2 for a Schrodinger equation, then its linear combination psi 1 plus psi 2 or a psi 1 plus a psi 2 will also be a solution of the same Schrodinger equation. You will understand that later when you study about study with some examples. So when you have a Schrodinger equation with a solution psi and another solution which is psi 2. First one solution is psi 1, second one solution is psi 2. Then its linear combination also will be another solution. So you can consider infinite number of solutions for that same Schrodinger equation if you have two wave functions which are solution of that equation, that Schrodinger equation. Okay, now if you have a linear combination psi is equal to a1 psi 1 plus a2 psi 2, where a1 and a2 are constant, the above equation suggests that it is a linear property of the Schrodinger equation. So it is a property of the Schrodinger equation. If you have one Schrodinger equation and it has two solutions, psi 1 and psi 2, then it can have infinite number of solutions which are the linear combination of these two, psi 1 and psi 2. Understood? So this is the linear property of Schrodinger equation. Now psi 1 and psi 2 follow the superposition principle. Superposition principle means it is the linear combination, that is what it says, superposition. If P1 is the but now let us consider the probability. So if P1 is the probability density corresponding to psi 1 and P2 is the probability density corresponding to psi 2, how will you find probability density? Probability density, if you have given a wave function psi, its probability density is psi modulus square. That's all. That is psi star into psi. If it is complex, if psi is complex, then take the conjugate, complex conjugate psi star, and multiply it with the psi itself. you will get psi modulus square, and that is the probability density of that wave function. So the probability of density of this wave function psi1 and psi2 are, you cannot say that it is linear property is not there for the probability density. That is, you cannot say that probability of psi1 which is p1 and probability of psi2 which is p2, when you add these two you cannot get the probability of psi1 plus psi2. So that is not linearly dependent. So that is what we are going to check. So then if you see, if you have wave function psi is equal to psi1 plus psi2, due to superposition principle, total probability will be, how will you get the total probability? Superposition principle says that if you have two wave functions, when you add these two, it will have probability density which is the modulus square of that added wave functions. So that is P of wave function psi is equal to probability density of wave function psi is equal to psi modulus square. Understood? That is psi, which is psi1 plus psi2. Psi1 plus psi2 modulus square will be the probability density of wave function psi. Okay, now psi1 plus psi2 modulus square means psi1 plus psi2 star psi1 plus psi2. Psi1 plus psi2 star is psi1 star plus psi2 star into psi1 plus psi2. So if you multiply, you will get psi1 star psi1, psi2 star psi1, and psi1 star psi2, and psi2 star psi1. So we have here the probability density of wave function psi is equal to P, which is equal to psi1 star psi1 is P1 and psi2 star psi2 is P2. So P1 plus P2 plus two additional terms are there. So P is not equal to P1 plus P2. There are two other terms also. Two additional terms are there. So we cannot say that probability density is linear. It can be added linearly. Probability density we cannot add linearly. Remember this. Okay. So linear property of Schrodinger equation we know, and psi1 and psi2 follow the superposition principle. Psi1 and psi2 follow the superposition principle means if you have two wave functions added psi1 plus psi2, its probability density is psi1 plus psi2 modulus square. That is what superposition principle says. Linear property means, linear property of Schrodinger equation means, if you have two wave functions psi1 and psi2 are as the solution of a Schrodinger equation, then its combination, its all linear combinations, a1 psi1 plus a2 psi2, all the infinite number of combinations are also solution of the same Schrodinger equation. That is linear property of that Schrodinger equation. Understood? Okay. Now let us go to expectation values. What do you mean by expectation value? Expectation value of any quantity. If you find if you want to find expectation value of any quantity, if here we say that f of x, it's a function of position, then how will you find that? It is the integral of f of x psi modulus square. That is, if you take the for example, if you have a system, you want to find its momentum's expectation value. So P expectation, momentum's expectation value you want to find. So you want to find what is the momentum, its expectation value in that system. So we just take the wave function of that system and then take the modulus square and multiply it with the P, momentum. Then take the integration with respect to position and take the integral minus infinity to plus infinity. The limit should be all over the space. So it should be minus infinity to plus infinity, provided the wave function should be normalized. If the wave function is not normalized, first you have to normalize it and then use that normalized wave function to find the expectation value. Okay, so if the wave function is not normalized, you just need to divide it with the normalization constant square. You have studied already how we do the normalization. So the expectation value here, now next f of x expectation we have written. If you want to find the positions x, position x expectation value, then x expectation, you do the expectation value symbol as greater than less than sign. Inside that you put the value which you need to find the expectation value. So here we are going to find the expectation value of position, that is x. So we are putting that x inside this greater than less than sign. So that means it is the expectation value of x. So expectation value of x is equal to minus infinity to plus infinity integral x psi modulus square dx. So this is the expectation value of x. This means, what does this mean? This equation, what does it mean? It is actually the average. So you find the position of a particle. For example, if you are finding the expectation value of position, then you are finding the position of a particle in a system several times and take the average of it. That is what it means, expectation value of x. Expectation value is the value of x we would obtain if we measured the positions of a large number of particles described by the same function at same instant t and then average the results. So that is what it represents. If you have a number of particles, instead of one particle, you should do the position measurement of large number of particles and then at some instant t at different times. First you take the position of large number of particles at an instant t and take many times, then average it, and the results will give you the position expectation value. So here an example is given. Find the expectation value of position of a particle having function psi is equal to ax, and you have to find the expectation value between the limit 0 and 1. X varies from 0 and 1. So you have to put not full space, you have to put the limit instead of minus infinity to plus infinity, you have to put the limit 0 to 1. Expectation value of x is equal to integral 0 to 1 x psi modulus square. X is ax. So substitute for the wave, x alla, psi and ax. Wave function is given as ax. So you substitute for psi modulus square as, it is not complex, so it is just psi square itself. So a square x square. So a square x square integral it is x square. X square into x varumba x cube varum. So a square into x square x, that is x cube. So integral 0 to 1 x cube dx is x raised to 4 by 4. Putting limit, the value of expectation value of x is a square by 4. So to find the expectation value of position of a particle having wave function ax in the limit 0 and 1 is equal to a square by 4. What is a there? A is the constant there, which is there in the wave function. Now operators I will teach you in the next class.